Ho 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 my dear Nephele addicts. This video showcases the work accomplished at Inria over the past few months, highlighting advancements in hardware and network architecture, with a particular focus on the integration of the VO stack. If you recall the global application graph presented earlier, we will only focus on a specific part, now visible on your screen. At the end, the video concludes with a demo. Let's start with the general organization of our code and the Git repositories. Code and repository organization. We so far have 5 Git repositories. 2 are dedicated to the web application named Network Planner and Controller. The first repository is based on the Flask framework for the API, and the second is based on the Vue.js framework for the front end. One repository is for managing PyCom devices, primarily developed with MicroPython. These PyCom devices will communicate with the gateway through MQTT. The Nephele VO repository is a simple fork of the repository developed by NTUA. We added some improvements to meet some of our use case requirements. The last repository is Python-based and primarily structured around the VO stack. This code handles our gateways and their associated virtual objects. In this video, we are mainly going to focus on this last repository, the VO stack code. In this central repository, Poetry is used to manage dependencies. The code is divided into 4 main parts: the gateway, the virtual gateway, a subpackage containing generic tools and generalized methods, shared by both the physical gateway and the virtual object, scripts and tools for managing local Docker containers. These also include Python scripts to simulate interactions with the web application, emulate PyCom devices, and replicate robot and drone actions. The physical gateway. As a reminder, the gateway runs on a Raspberry Pi and is entirely based on the VO stack, so, of course, it includes 3 key files: the configuration, the thing description, the Python runtime. Additionally, the physical gateway includes a subpackage named SQLite, which manages local data storage. This enables the lifecycle management of registered nodes and their data. Thanks to this feature, data is always stored locally in an SQLite database before being transmitted to the VO. The gateway supports 5 actions, all related to the node lifecycle. A node's lifecycle is defined using an enumeration class. A node can be in one of the following stages: registered. The node has been selected by a user via the web application. Deployed. A robot has positioned the node in the field. Running. The node is active and transmitting data. Not allowed. The node has been temporarily disabled. Any incoming data from this node will be ignored by the gateway. Unregistered. The node has been removed from the gateway and no longer appears in the list of referenced nodes. In error. This stage is triggered automatically when the VO or cloud system detects an issue, such as the node being unresponsive for an extended period. Now, let's return to the thing descriptor. You may notice that no properties are defined yet. This is because, in our use case, the gateway can dynamically connect and reference multiple nodes, either through human interaction or machine interaction. To handle this, we extended the VO stack to dynamically create new properties. In this context, a property represents a node. We will see the results of this functionality in more detail shortly. One of the gateway's important functions is its ability to send events to the VO to notify it of new node data reception. The virtual gateway. The virtual gateway is directly linked to its physical counterpart, as specified in its configuration file. This VO serves 3 primary purposes: Configuration proxying. It facilitates interaction between the web application and the physical gateway by proxying the physical object's actions. Data handling. The virtual gateway receives and processes new node data. This includes storing the data in an InfluxDB database and instructing the physical gateway to clear its SQLite cache. Dynamic alert generation. It runs a rule engine to generate dynamic alert events. An alert is essentially an event generated by the VO, containing information such as the node, sensor type, current alert value, etc. The rule engine. To manage multiple rules to trigger dynamic alerts, and to support our real-world dynamic use case, we are generally using the approach to handling rules and alert events. To achieve this, we are developing a flexible rule engine. As you can see in the highlighted part of the code, a single rule is statically defined. A rule is an object with three properties. The first rule property is the sensor type, which is the type of sensor whose value you want to check. In this case, the rule applies to a sensor measuring temperature. The second rule property is the comparison operator. This is a restricted operator used for comparison. Currently, only these following operators are supported: greater than, less than, equal, greater or equal, less or equal. The last rule property is the threshold value. The threshold value is the value against which the sensor's reading will be compared. In this example, whenever the virtual gateway detects a temperature greater than 35.1 degrees, the rule is considered valid. Once validated, the virtual object triggers an event named newAlertEvent, using the information stored in the rule object after its execution. As demonstrated in the following method execRuleEngine, we also designed a simple efficient rule engine to manage all defined rules. When the engine runs, it evaluates each rule and returns a dictionary indicating the validity status of all rules, so multiple alert events could be very easily triggered. Currently, as demonstrated, the rule engine operates with statically defined rules. However, we are developing actions to enable dynamic operations on these rules. These actions will be integrated into the VO thing description and will allow users to create, read, update, or delete rules. Once these features are implemented into the virtual gateway, alert rules can be managed directly from the web application, enabling adjustments through human interaction or automated processes. Folks, I can feel your impatience to see all of this in action. So, to wrap up this video, let's kick off a quick demo by running the entire stack. First, we'll start the physical gateway. As you can see, the starting logs are being printed. Next, we'll start the virtual gateway and see the same kind of logs. Once these scripts are launched, we can now interact with the published VO stack actions. Here, we'll list the registered nodes. Since this is a fresh physical gateway, no nodes are referenced yet. Now, we're going to emulate an action call by the web application where a user would reference a node named Node 3. This action would typically be called during the mission configuration. This script emulates that. At this point, Node 3 is listed by the action getAllNodes. The output of this action contains some information about the new node, specifically its status, which is currently registered. The status is also stored in the local SQLite database. We can then observe that no data has been received yet. To accept new data from a node, it must first be deployed on the field by a robot. We'll emulate the call of this action by running another script. The database is, of course, updated accordingly. To simplify this demo, we will also emulate our Python devices. we launch a script that publishes data coming from the sensor of the node 3. PyCom data are published into a MQTT topic, following the architecture of the VO stack. Here you can see in the logs of the physical gateway that every new data coming from the node 3 is stored in its local SQLite database. Because there is a perfect and good connection between the physical gateway and the virtual gateway, the SQLite storage is cleared by the physical gateway after being received by the virtual gateway. That's why we see only one data waiting, but we cannot see it in the database because it's immediately removed from the SQLite database. If we have a look at the VO side, we can read log confirmation messages coming from the remove data action call. If we wait a bit, we will see an alert triggered because of the execution of the rule engine. We presented before this rule engine. Now, let's simulate a situation where the virtual gateway is not reachable by the physical gateway. You can see that the local storage size of the physical gateway is increasing as new incoming data is stored in its database with the status value waiting. Once the virtual gateway comes back online, it receives the previously stored data from the physical gateway and then instructs the physical gateway to clear this data from its cache. If you take a closer look, you'll notice that 6 data points were received retroactively and subsequently removed from the cache of the physical gateway. Upon checking the database, you can see that the table is now empty. Finally, since node 3 has been sending data, its status has automatically changed to running. If you call the getAllNodes action again, you'll also see the most recent data received from node 3. As mentioned earlier in the presentation, the VO is capable of receiving data retroactively from the physical gateway. To enable this functionality, we made adjustments to the InfluxDB write method in the VO stack repository. Now, any historical data is stored in the InfluxDB database based on the timestamp of when the sensor sample was collected, rather than when the data was received by the VO. In this short demo, you can observe data being written into the InfluxDB database of the virtual gateway. You could imagine the graph being completed retroactively by filling in the missing points. Here, we want to showcase the modifications made for dynamic property registration. As you can see, Node 3 is listed as one of the properties in the online catalog of the physical gateway. If an action to unregister the node is executed, the property Node 3 will be dynamically removed from the JSON array property. Conversely, it can be re-added if the register action is called again. To end up the section on the VO stack, we want to demonstrate the alerts generated by the rule engine. As a reminder, there is currently only one rule implemented to trigger alerts. These alerts are published to an MQTT topic, following the VO stack naming conventions. Each time a rule is validated, an alert event is sent to the topic. As visible in the right side of the screen, in the MQTT desktop client, we also created a simple Python converter to convert a rule and its validity status into an MQTT alert event. It could be used to handle any gateway, any node, any operator, and any threshold to generate dynamic alert. In the very near future, subscribing to this topic will allow the web application to receive live alerts seamlessly. We've now wrapped up the hardware and VO stack sections. To close this video, we're excited to share an early draft of the front-end design mockup, created using Figma. Please keep in mind that this part is still under development. The front end is designed to guide users intuitively through the mission setup process. First, users can select the type of mission they want to undertake. Next, they can choose the devices to be used during the mission. Afterward, they'll specify the types of nodes required for the operation. They will have the option to activate sensors individually for each node. Finally, users will be able to complete the configuration and launch the simulation. While we've made good progress on back-end development, we're also focused on refining the data model to ensure smooth integration and deliver a cohesive user experience across all components. So here's a quick look at the database model currently implemented and handled by the Flask-based backend API. Thank you for your attention. I appreciate you taking the time to listen to this presentation. If you have any questions, feel free to ask.